Pedro Espino, who got his PhD from the University of Arizona, and now he's one of the N3AS PhD fellows. And he will today tell us about the fate of twin stars on the unstable branch. Go ahead, Pedro.
Thank you. Yeah, so today I'd like to tell you about a short project where we considered the evolution and fate of twin stars on the unstable branch. And this project has set the stage for some new work, which I'll delve into a little bit at the end. So I'll start off with an introduction. I'll take time to explain each of these keywords, and you can follow along where in the talk I am by looking at this top brace up here. But before I get to each of these keywords, I'll just provide a bit of background on what it is we're dealing with, specifically starting with the dense matter equation of state. So this diagram is probably familiar to many of you. This is the QCD phase diagram, where on the vertical axis you have a proxy for the density in a system, and on the vertical axis you have the temperature. You can see regions where we have different phases where we expect to find different phases of matter. In the typical densities and temperatures we're used to dealing with here on Earth, matter is confined to hadronic states. And there are two kinds of phase transitions you can have given asymptotic freedom, where if you increase the interaction energy or the energy scale in the system, you expect to find at very high energies your degrees of freedom as no longer hadrons, but weakly interacting quarks. You can increase this energy scale by increasing the temperature, right? And as you do so, in the end, you, at very high temperatures, get to a state of a quark-gluon plasma. But the type of phase transition I'm interested in, and that's more relevant to compact stars, is at low temperatures by instead compressing matter to extreme densities. And this one's a bit more uncertain, where, well, we know that at low densities, close to up to 2 times the saturation density, where the saturation density is given up here, matter is found in this hadronic state. And at very extreme densities, well above what you may find in the center of compact stars, you could expect to go into the perturbative QCD realm. But this intermediate region still remains largely unknown. And it's possible that at the densities relevant to compact stars, say something like 4 to 7 times the saturation density, you could get a state of quark matter. Again, we're in the realm of asymptotic freedom, right? Your system is now composed of weakly interacting quarks. The intermediate range between a hadronic state and a quark state is the region that has most uncertainty in modeling today. And typically what's done in order to treat these kinds of equations of state, or equations of state that capture this phase transition, is to model the nucleonic phase and quark phases separately and find some way to match and interpolate between the two phases. So here's just a quick schematic of exactly this, where this gives you an idea of how these kinds of equations of state are modeled. You take some hadronic equation of state up to about 2 times the saturation density. If you extrapolate that to the densities relevant to the centers of compact stars, you get very large uncertainties. And similarly, given a quark matter EOS, if we extrapolate to lower densities, we get significant uncertainties. So typically what's done is to consider separate models for hadronic and quark phases and find some way to match between the two. And I'll go through the next few slides quickly, given the nature of the audience here. But I'll just give some examples of equations of state models for these different regimes or density regimes. In the hadronic regime, 2 popular approaches are the many-body approach and also the relativistic mean field approach, where in the many-body approach, basically you're taking the understanding we have of symmetric nuclear matter and pure neutron matter near saturation density and extrapolating it to arbitrary proton fraction so that you can get to more realistic descriptions of neutron star matter. Kind of more first principles approach is to write down an effective field theory for the degrees of freedom you expect at these densities, which In the case of neutron stars, are nucleons and some leptons, electrons and muons. So given such an effective field theory, you work within the mean field approximation, where you integrate out any of the mediators here, and you can extract an equation of state, where, just to be clear, what I mean by equation of state, when I refer to the equation of state throughout the talk, is this pressure density functional. In the quark phase, just to give you a flavor of some models that are used today, you can have things like bag models, which essentially model the quark phase as a gas of weakly interacting or a non-interacting Fermi gas with energy density given here, equation 4. And then you account for the energy density required to have that bag in space. And this is parameterized by this bag constant B. So it's a very simple equation of state, or simplified equation of state. Again, a more first principles approach is where you can write down an effective field theory for the degrees of freedom you expect, which in this case would be quarks. You let them interact by exchange of bosons. And again, you extract an equation of state in the mean field approximation. As I alluded to earlier, the intermediate region remains the most uncertain. One, in terms of extrapolating or interpolating between the low density hadronic and high density quark equations of state, but also in how you treat the phase transition, because this is where you expect the phase transition to actually happen. And generally, to treat the phase transition, there are two ways in which it's done. You can impose a local charge neutrality in the system. And this really, what this ends up meaning is that your electron chemical potential is discontinuous across the phases, moving from one phase to another. In terms of, or for equilibrium stars, what this means is that you have, for example, in some equilibrium hybrid star, you may have a dense core surrounded by an envelope of nucleons, and a very sharp interface between these two regions. You could also impose a global charge neutrality on, in this case, the entire star, right? That's our system. And really the difference is you now have continuity in the electron chemical potential across phases. And this, for equilibrium stars, means that you can have regions of mixed phases. So before moving on to stars, I'll just quickly draw your attention to this recent study where, so we've seen that, you know, there's a lot of modeling that can go into producing these equations of state, and there remains a lot of uncertainty or model dependence, I suppose. And this study took a kind of model agnostic approach at constraining the equation of state, or whether this phase transition even happens, where at low densities below 2 times saturation, they fixed some nucleonic equation of state. And at very high densities, well beyond what you expect in the center of compact stars, they assume that this equation of state goes to the perturbative QCD realm. And in the intermediate region, they allow complete freedom except for imposing causal constraints. And they also impose this constraint that each equation of state should produce at least a 2 solar mass neutron star, or star, I guess a hybrid star. We have a question here. Yes, Susan.
Very much. Thank you very much. I guess I'm questioning about the perturbative QCD limit, because although individual quarks can be very close together, because the medium is ultra dense, you could imagine that there are long range forces that are not perturbative in nature, that you still could. And so I guess I'm just wondering at that ansatz, maybe if you have any support for it. I mean, any lattice studies that suggest it's right, or I guess
Sure.
not even a meaningful comment on my part. Sorry, not lattice stuff. I'm wondering what you would think. I mean,
yeah, I'm not sure as to how justified this assumption is. But again, I want to emphasize that these are densities well beyond what you expect at the center of stars. So these are very extreme densities where, you know. I
guess I'm wondering because it's not an obvious limit to me, But
Mhm.
nevertheless, it seems to come out of these numerical simulations that you're considering. And so I wondered if you had, I guess maybe it's just cart and horse. You've already imposed that. Okay. So anyway, I'm asking a question about it. Maybe we can't answer it now. I just wanted to raise the issue. Thanks.
Thank you. Yes. So yes, in this particular study, the authors, the main astrophysical constraint that was imposed on these equations of state was to produce a compact star of at least 2 solar masses to be consistent with the heaviest observed neutron stars. And you can see that there remains a lot of variety in the equations of state you can have. And if you kind of squint, you see this two-phase structure. But suffice it to say that equations of state with high density phase transitions, of which I mentioned a bit in the past few slides, are completely viable from an astrophysical perspective. So now I'll turn to twin stars. And one of the earliest references I could find on this was this paper by Ulrich Gerlach, titled "The Equation of State at Supernuclear Densities and the Existence of a Third Family of Superdense Stars." So the third family here that the author is referring to is in the context of the 2 other families of compact stars, the white dwarfs and the neutron stars, where the white dwarfs have compactness of about 10 to the -4, or dimensionless compactness, and neutron stars are much more compact at about 0.2. If we allow for a high density phase transition, it's possible that you have a third branch of equilibrium stable stars, where the centers are no longer supported by nucleon degeneracy pressure, but instead quark degeneracy pressure. And these are expected to be more compact than neutron stars. And if we zoom in, so what you're looking at here, just to clarify, is the mass radius diagram, for a schematic of the mass radius diagram for these 3 branches of stars. And if we zoom in a region of this, we can see that for a given equation of state that has this high density phase transition, you can have hybrid stars that have the same mass, or third family stars that have the same mass as neutron stars, but are more compact. And this is what I mean by a twin star. So I'll pull a quote from this paper where I got this plot. Due to the partially overlapping mass regions of the neutron star branch and the branch of the third family, it is possible that non-identical stars of the same mass can exist. And such pairs are referred to as neutron star twins. So throughout the talk, when I refer to a neutron star twin or twin star, I mean a hybrid star with the same mass as a neutron star, but smaller radius. Now I'll briefly turn to stability of these objects. So going back to this plot, you can see that, well, in black, we have some equilibrium, well, the 3 branches that I referred to earlier. But separating these 3 equilibrium branches, there are also sequences of unstable stars. That is, stars that reside along these red tracks are expected to be unstable to different modes excited in the star. Here you can see which modes are expected to be unstable in which star. And I'm particularly interested in the segment between C and D here. These are the unstable twin stars. They have densities above that for phase transition, and are expected to be unstable to different modes. For the remainder of the talk, I'll focus on 2 of these kinds of equations of state. And here you're looking at the mass radius diagrams for these 2 equations of state, the A4 and T9 EOS, as I've labeled them. And if I draw a line of constant mass through the space, you can see it intersects this MR diagram at 3 points, right? The rightmost being a neutron star, a stable neutron star, the leftmost being a stable hybrid star, and this intermediate point being what I'm interested in, an unstable branch hybrid star. These stars are expected to be unstable from the perspective of the turning point theorem, which states that for a sequence of stars of constant entropy and angular momentum, an instability to radial perturbation arises when this criterion is met. So what you're seeing here is exactly that, a sequence of stars of constant entropy and angular momentum for these 2 equations of state, specifically the mass as a function of energy density. And I've highlighted the segments where this criterion is met in pink. So these are the stars I'm interested in. Now, why am I interested in these stars? Well, this is just an explanation of the title, but by this point, hopefully it's clear what I'm considering. But why am I interested in these objects? Well, before this study, it wasn't, the end state of this instability was not well known in the context of hybrid twin stars. And there are two possible end states for this instability, right? Because at a given mass, it can transition to the stable neutron star branch or the stable hybrid star branch. And this could have possible implications for how these stars are formed in a dynamical astrophysical scenario, if they're in the twin star regime. But other interesting questions we could try to answer are, what are the dynamics that we can expect from the transition of these objects to a neighboring stable equilibrium? And are there any interesting signals we could expect from these dynamics? So to try to answer these questions, I'll briefly highlight the methods we took, or the methods we used to try to answer some of these. Starting with the equations of state. So just to give a bit more context, we're going to try to answer these questions using three-dimensional GR hydro simulations. But if you consider that our two equations of state, they were constructed using the Maxwell construction. So we have a very strong first order phase transition where the sound speed is 0 over a range of energy densities. And this is troublesome for stable long-term numerical evolutions. So the first thing we did was to take our base equations of state and modify them. We fit them with piecewise polytropes, and that gave us control of the sound speed in different regions of the energy density. Specifically during this phase transition here, we've increased the sound speed so that it's non-zero. And we tried to keep it as small as possible, but just finite. Given these modified equations of state, we construct initial data over a variety of different models, and we evolve them using our three-dimensional GR hydro code. So we begin all evolutions in one of three ways. We either don't perturb the star at all, which I refer to as equilibrium evolution, or we change the pressure slightly. We either increase the pressure, positive pressure perturbations, by up to 1%, or decrease it slightly everywhere in the star by up to 1%, just to ensure that these perturbations that we actually see to excite the instability are small. Our set of initial data, just to kind of review before I get into the results, covers two equations of state with different properties and different masses, basically. So we have a wide range of masses in our set of initial data. So what you're looking at here is, again, sequences of constant angular momentum for two equations of state. And as I increase the angular momentum, you can see with this color bar, the sequences move upward. So they allow for more massive stars. And I've marked our initial data, our initial configurations in these simulations with dots. You can see that I have both non-rotating and rotating models here. So I'll quickly review the kind of general result here. I'll show a quick animation. And what you're looking at here is a slice on the equatorial plane of the rest mass density, this main panel. And the quarks are shown in white here. To the right of that, you have the rest mass of the star as a function of the central rest mass density. And this allows us to track the model, which is marked by this dot here, in reference to the equilibrium sequence for this equation of state. And the lowest panel shows the maximum rest mass density as a function of time. And what you'll see is that initially the model contracts and the size of the quark core grows. And as more and more matter enters this quark phase, which is at higher pressure, eventually there's enough pressure there to revert the model into expansion, and the momentary collapse halts. But one thing you can observe is that the central region is oscillating, and initially oscillating quite strongly between the two phases. Eventually, these oscillations do die down over time. as the model tends toward the lower density equilibrium. It tends toward the neutron star branch, and these oscillations are dissipated. But in doing so, and moving toward the neutron star branch, this model can undergo strong oscillations and a revival of the core for some amount of time. And this is what we find across equation of state and across different masses for the initial configuration. So what you're seeing here is the rest mass density as a function of time for the two equations of state. These two models on the left are for the A4 equation of state and the other for the T9. And each of these have different masses. But you can see that it's the same qualitative behavior, an initial contraction or momentary collapse of the model, followed by some oscillation. And eventually the model settles toward a lower density equilibrium, toward the neutron star branch. Depending on the exact properties of the model, these oscillations can persist for longer or shorter amount of time. It turns out that if we actually, so there are two sets of curves on each of these plots. The solid line corresponds to the equilibrium evolution where we don't perturb the star, and the dashed corresponds to positive pressure perturbation. We slightly increase the pressure at the start of simulation, and regardless of that, you see the same qualitative behavior. Instead, if we slightly decrease the pressure, we find that we could incite these oscillations for an extended amount of time, depending on the model. You can see that the oscillations persist for slightly longer than previous cases, but in the end, the models do settle toward the neutron star branch. Now, I'll show results in the case of rotating models. You see the same qualitative behavior here. So again, we're looking at rest mass density as a function of time. Moving from left to right, I've increased the angular momentum in the star. And you'll see, again, strong oscillations to begin with, and essentially a dissipation of these oscillations as the model settles toward the neutron star branch. But here we have a strongly oscillating star, at least for some amount of time, that is rotating. And this could be an interesting source of gravitational waves. And in some cases, you actually get a very strong revival of the core. And just to emphasize, these oscillations are driven by the phase transition. So if we consider the gravitational radiation as a function of time, one interesting characteristic feature about these waves is that they have a kind of burst nature to them. So these are, what you're looking at here is a dominant polarization in the gravitational waves as a function of time, extracted from our simulations. You can see that initially, before the model begins to oscillate, the waves are small, but as the model oscillates between these two phases, as the central region oscillates between these two phases, you get a strong emission of gravitational radiation. And eventually this dies down as the model settles toward the neutron star branch. It turns out that these bursts of gravitational waves could be detectable if the sources are close enough. So here, assuming a source that is galactic or about 10 kiloparsecs away. And here I'm also, well, you're looking at the characteristic strain in the frequency domain. So two things to note here. One, the sources may be detectable at future generation detectors, and also that they have a characteristic frequency of oscillation of about a few kilohertz, as expected for F-mode oscillations of neutron stars. And this becomes a very interesting potential source of gravitational waves, a burst source, when you couple it to possible progenitors of these systems. So one thing I'm looking into now is to try to incite these strong oscillations driven by phase transition in a white dwarf neutron star merger, where the in-spiral waves are expected to be much lower than these characteristic kilohertz waves. And yes, so that is where I'll conclude. We've explored the stability of hybrid hadron quark stars. We've seen that they tend to migrate toward the stable neutron star branch, regardless of the particular equation of state we use or the initial mass of the model, and also the initial perturbation we see in the star. But in migrating toward the neutron star branch, they oscillate strongly, and these oscillations are driven by the phase transition. And in the case of rotating hybrid stars, you can have an interesting burst of gravitational waves associated with these stars. So along with this white dwarf neutron star binary project I've started, I'm also considering eccentric hybrid star mergers to try to dynamically incite these oscillations during an in-spiral to see if they could also have some imprint on an in-spiral waveform, for example. So I'll stop there. Thank you for your time, and I'm happy to take any questions.
Thank you very much, Pedro. We have a lot of questions, so maybe I'll start some from the chat. I don't know if Evan wants to ask his question, or I can also read it.
I can ask it. Thank you, Pedro. That was a really informative talk. I had just something very basic. When you started talking about these three classes of stars, white dwarf, neutron star, and then this quark-like star, I was just curious, like, where is kind of that boundary between, the end of the neutron star and then black holes? I've seen a lot of these plots, right, with like different equation of states showing in the mass radius kind of space, and that causality line in the top left. Some of these, depending on the equation of state, they get really close to it. So I was just wondering.
That's a great question.
How that fits in.
So I would say that depends strongly on the particular equation of state you use to model the quark phase and the phase transition. So typically, well, in particular, the ones I use for this study don't reach that causal limit. So so that is something you have to be careful of when modeling this phase transition, that that your stable branch doesn't break into the causal area.
So does this require like a stiffer equation of state?
I suppose so there's a softening of the equation of state when you have a phase transition of this sort to quarks. So if you want to produce something like a 2 solar mass neutron star, you can stiffen possibly your hadronic equation of state, but it's not easy to say whether or not you should stiffen the equation of state to avoid the causal limit or soften it, or
All right, thank you.
Sure.
We have also a reply from Santi and George, but maybe these two from chat can be left to the discussion, and then I'll move to share with question. Do you want to unmute yourself, or should I read it?
I'm sorry. I couldn't hear too well. Sorry.
Yeah, and there are also some replies from Sanjay and George, but I think we will leave them to the discussion, and I will move on to the shared question. Cheryl, do you want to unmute yourself, or I can read it?
Yeah, sure. Thanks, Pedro, for the talk. I had a couple of small questions. The first one was when you talk about how you had to sort of tweak the discontinuity in order to make it numerically possible, right?
Yes.
Have you played with how strong that tweaking is, and does it have noticeable impact on the results?
Yeah. So basically, my philosophy going into this, or this particular part of the project, was to modify the equations of state as little as possible. So I just systematically increased the sound speed until I found a stable evolution of a star that I expect to be stable. So I consider both stable hybrid stars and stable neutron stars, and ensured that their evolution was stable with these modifications. So these are basically minimal modifications that allow for a finite sound speed and stable evolution. But it does affect the evolutions of these stars. I mean, you can almost make the phase transition disappear, right, if you're not careful in some ways.
Okay, so if we were to double the size with which you perturb it, would that be qualitatively different, or would it just be some tiny perturbation on the results?
Yeah, it depends. Yeah, if we were to double it, yeah. So what I would expect is larger oscillations in the rest mass density for stable stars. This could have this could affect the oscillations, the initial oscillations, I suppose, or initial evolution of this model. But yeah, that's a good question. I can look into that in a more systematic way, I suppose. See exactly how much these oscillations change with, for example, a double.
Yeah, yeah. I think that would be really interesting.
Yeah, thanks.
And I'll let George go for my other question.
George, do you want to unmute yourself?
Yeah, thank you, Pedro. It's a very intriguing talk. I had this question. So two questions really. So the first is and maybe they're related, what's damping those oscillations? They damp out quickly. Is it just gravitational radiation reaction? I would imagine that's small.
That's a great question. So my initial suspicion was that it was like thermal shocks in nature, but having a closer look at the simulations reveals that the temperature does not spike. You don't really have shocks developing here.
Then my second question was related to this. Really, do you get any neutrino emission? Kind of a quark Urca process or something, because you're changing the density and the Fermi levels.
I would love to answer that, but this version of our code didn't account for neutrinos. But that's a great question. Yeah. To kind of follow up a bit on your first question, there was a paper I found by Sophia and Mark Alford, where they showed analytically that you can have dissipations of these kinds of oscillations just from a phase offset of, I guess, the frequency at which the interface between the quark and hadronic regions.
Sure. I mean, your stress energy tensor that you wrote down, I mean, it isn't necessarily diagonal. There could be shear stresses.
Yeah. So I think the dissipation could be that, but it's hard to show from a GRHT simulation given the coordinates and the ambiguity in coordinates there. But that is something I want to look into a bit more, just to kind of track exactly the surface here and see the frequency of oscillation and see if there's a kind of phase offset between that and the frequency of rest mass density or pressure oscillations.
Very good, fascinating.
Yeah.
Okay, I think Dake was next. Dake, if you want to unmute yourself.
Yeah. Hi, thanks for this very nice presentation. So I probably have two questions and a comment about an early discussion. So first, if I think from a stellar evolution point of view, those hybrids unstable stars probably form from supernova. So when they're formed, well, they have a velocity fraction of c. So do you think that could be sufficient to? So in those scenarios, would it be possible that the quark part wouldn't be able to support the oscillation?
Right.
You support the collapse and then just all the way falls to the quark branch.
Yeah, that would be, that's an interesting question. And hopefully these studies where we have a dynamical kind of inciting of these oscillations would try to answer that in a better way, but it's hard to say from, we start from an equilibrium or a non-stable equilibrium sequence that we perturb to something as dynamical as a core collapse supernova. But yeah, that is interesting to consider. Yeah. Okay. I mean, I've mainly been focused on these white dwarf or inciting these oscillations through white dwarf neutron star mergers, but it could also be interesting to see what happens in the formation of these objects following a core collapse supernova, if that's possible. Yeah.
Okay. Yeah. Thanks.
Sure.
My second question is sort of related to George. So, so those unstable modes, sort of by the zeroth order analytical study, are characterized by those exponential growth in those instabilities, but you have some sort of damping. Yes. So yeah, could you maybe repeat your answer earlier? So what do you suspect to be the so as I understood, those off-diagonal terms in the distribution terms are not added in your simulation, right? So
Right.
what was your suspicion on the damping source?
Right. Yes. Yeah. Well, what I suspect could be happening is that, yeah, basically I alluded to this study where it was shown that if there's a phase offset between, I guess, the oscillations in this interface itself between the quark and hadronic regions, and the oscillations in the pressure, this alone can dissipate energy. Perhaps Sophia could give a bit more detail. I mean, she was.
Yeah, maybe I can just say a bit more on this. So imagine the boundary between the two phases itself is oscillating, and that causes a lag between the equilibrium configuration and the temporality where the boundary is. So basically, because the weak equilibrium at the boundary needs time to be restored, that phase lag will cause dissipation. And when we studied a different environment, it's not this dynamic oscillation, but in a cold neutron star, where the density undergoes a smaller amplitude oscillation.
Mhm.
And we found that phase conversion between the two phases at the boundary is strong enough to damp that amount of oscillation. And it will be interesting to see here whether in the more realistic simulation work like Pedro shows here, and how effective that damping is going to be look like.
Yes.
Yeah.
It's very interesting. Yeah, it's definitely something. I mean, I can go back and have a look at trying to track this interface. But again, there's some ambiguities with the coordinates here, right? And what exactly it is that I'm tracking, I suppose. But yeah, but yeah, I could have a look at that. And yeah.
Yeah, okay. So my last question regarding the early discussion on the causal limit. So wouldn't so I would assume as long as the equation say it is it is causal, the maximum sound speed is less than 1, the TOO equation will automatically guarantee that the equilibrium solutions are within the causal limits, right?
Correct. Yes.
Okay. So you don't need to worry anything about the phase construction or.
Right.
Okay. Thanks.
Correct. Yeah.
Okay. We also have a question from Susan.
Thank you very much. Yeah, I just wanted, maybe I was intrigued by this Gerlach paper, the first suggestion of the third family from 1968.
Yes.
Now that predates the discovery of quarks at SLAC, though of course it's after the Gell-Munz Eightfold Way. So maybe you could tell us a little bit about what he had in mind for the third family, and maybe also the broader question of whether you really would need to have a quark-gluon phase transition in order to realize such a third family.
Yeah, it's a good question. So I guess I'll try to answer the second one first. I don't think a quark-gluon, specifically a quark phase or a transition of this kind, is necessary to have a third disjoint family, as long as you have some kind of phase transition that in the end effectively softens your equations of state at high densities.
Oh, so it could be hyperonic. It could be just a strange hadrons, perhaps.
Yeah, I suppose a strong enough hyperonic phase transition of sorts, if it happens at high enough densities. Well, it could also happen at low densities, I suppose, and you'll just have lower mass hybrid stars. Yeah.
Okay.
Yes.
The
And
key input is that discontinuity itself. You do not need to specify what the true phase is at ultra high density. And this sort of third family stars can be found in other equation state with kaon condensate, something like that. It's not necessarily being quark phase.
Perfect. So that answers that question. And so what did Gerlach have in mind?
so, I mean, going from the abstract itself, well, I suppose it's just some other kind of degenerate matter that's not nucleonic. Yes.
So we had strange hadrons in abundance in 1868. So maybe this is perhaps a direction. So maybe worthwhile to look at the paper.
Yeah.
Thanks very much. Okay.
Now, Sanjay, do you want to ask a question?
Yeah, thanks, Pedro. That was a very interesting study. I may have missed this. I'm trying to understand what are the time scales here. So there's a time scale which is just, this is a radial mode of the neutron star. So I'm guessing the time scale is just set by the sound speed.
Correct. Yeah, so I plotted most things in terms of the dynamical time, which in the case of these stars is about a millisecond. So yeah, the oscillations can persist for, you know, a significant amount of time, but over about 100 milliseconds, typically they dissipate.
Okay. And is your perturbation on a star that was cold initially? Is this a zero temperature, close to zero temperature star?
Yes, correct.
So there's going to be a time scale associated with the kinetics of the phase transition, right? You know, just because you give matter higher pressure or higher density, it's not going to immediately go to that phase.
Right.
And are you assuming that it does instantly react to your perturbation?
Well, so the simulations themselves do not assume this. Basically, we have some kind of hybrid thermal treatment for any additional pressure that's not the cold pressure. But that, you know, in post-processing, I found that thermal pressure remains very low. So it turns out that throughout this evolution, the star pretty much tracks the cold equations of state with very small corrections above it.
Yeah, okay, but my point is that you may require weak interactions, for example, as Sophia was talking about, to even go to that phase. So the phase may require you to produce a whole bunch of strange quarks to be able to realize that phase. If not, it's just going to be in the nuclear phase because that's the phase that's favored. So I'm asking whether the phase transition kinetics is something that can be incorporated in your models.
Yes, I mean, these particular simulations did not account for any weak transitions or anything like that, but it is feasible to just account for these rates dynamically, right? Like you'll just see whether you'll keep track of the rates throughout the simulation and see whether the matter has actually transitioned to the core phase. But I think that would be a great follow-up, actually.
Yeah. I suspect that if you can introduce the weak reactions into your simulation, it will also account for the effect that Sophia was talking about, which is basically bulk viscosity.
Yeah.
And it's just so out of equilibrium, weak interactions will produce heat. And so I suspect that, you know, between you and Sophia, you guys can figure out how to include those weak interaction reactions, and that'll add a lot more realism to your simulations.
Oh, that's great. Yeah, that's very interesting.
Practically, I think the simulation will be able to track the local velocity of the boundary itself. And microscopically, that velocity is determined exactly as Sanjay said, determined by the rate of weak interaction. And also there will be diffusion of strangeness near the boundary. So those two are the determination, other ingredients that going to determine the motion of the boundary microscopically. But it will be really great to see in the simulation with that. I mean, by incorporating that changing velocity can make any difference here. Yes.
Yes, and it's certainly feasible to add this. I am working on some things with David now where we try to do something similar, but with pions.
Right, it's the same thing. I mean, basically, if you can connect a reaction network to your hydrocode,
Right.
you can understand this dynamics well.
Yeah, that would be a great follow-up to the study. Thank you.
I think we have one more question from Sherwood.
Oh, I'm so sorry. I forgot.
Sorry.
I lowered my hand, I thought. So
I thought Sherwood had another question. Sorry.
Yeah, I'm curious about the rotating models. Just do you know off the top of your head how the ratio between the kinetic energy and the gravitational binding energy is for these
I don't know off the top of my head. This lowest rotating model, well, the ratio of polar to equatorial radius for this one was very close to 1, so it's not very fastly rotating.
Okay.
But I can definitely get back to you with specifics.
Yeah, I'm just curious because I several years ago I did a paper where I saw some qualitative change in the with how the gravitational waves behave at a value of about 0.06 for the rotational about the potential energy.
Interesting. Yeah, I'll definitely get back to you on this.
Yeah, that's it. Thanks.
Actually, I also had one question. So you said that the unstable twin stars, they tend to evolve toward hadronic, so like neutron stars. So is there any other way that you could form such a twin star stable branch?
Yes, so as Dake mentioned earlier, it's possible that, with a strong enough, maybe a stronger perturbation, you could force the star to migrate to the stable hybrid branch. But it's hard to say definitively some dynamical formation channel for a stable hybrid twin star. If they cross into the unstable regime, it seems they prefer to go toward the neutron star branch. Yeah, so I'm not sure if there's a definitive way of forming a stable branch model. I mean, you could form a stable hybrid star, and based on this study, it would have to be above the twin star regime, with mass above the twin star regime, so that it could comfortably land in the on the stable branch without migrating to the neutron star branch.
Thanks.
But yeah, I'm not sure basically. Yeah.
Thank you. And then I think Sanjay had a comment to address first Susan's question. I don't know if you want to go back to it. It was to address Susan's question. Gluons acquire a mass because matter is a color superconductor at asymptotic density. This is not perturbative effect, but its impact on the equation state is so big because the pairing gap is much smaller than chemical potential.
That was meant to address a question Susan asked.
I thought that was a great answer, by the way. But nevertheless, it was just concerned whether or not it was suitable to consider a perturbative QCD limit for the high, I guess, with the equation of state, I guess, a high density.
Yeah, I mean, this was a question that I think a lot of people were worried about. And because you have Cooper pairing, these long-range instabilities are, this was work done, I think, by Frank Wilczek and Krishna and Mark and the Stony Brook group a long time ago. So it's actually stable. There aren't any long-range forces left, even at asymptotic density.
Okay. Thanks.
And there is also a reply from George to question about the black hole. We thought it was fourth family. So that was not releasing the vacuum from the centrals in the
Yeah, that wasn't the question. I was trying to answer Evan.
Yeah, I realized, George, it was kind of the way I phrased the original question was a little.
Yeah, these things are always on the.
Exactly. Yeah, that was what I was getting at, and I think Pedro addressed that really well. So there's no need for a follow-up.
Okay. Are there any other questions?
Can I ask a very quick, very simple question? Just out of curiosity, in these, how much energy is carried off by the gravitational waves signature?
Yeah, it's very little energy. I did do a calculation, but I don't recall off the top of my head. It's tiny.
I guess really what I'm getting at is it's not a particularly large fraction of a solar mass, so it's not like you see this star, it collapses in this way, and then you notice that its mass has shrunk by a tenth of a solar mass or something like this.
No, it's much smaller than that.
Okay, figured that would be the case. Okay, thanks, appreciate that.
Sure.
Okay, I think we don't have any more questions. So thank you very much again, Pedro, for a very nice talk. And we'll see hopefully everyone next week for the next N3AS seminar.